Hello, hi, welcome once again to the continuation of our series. This is Go-Gate Engineering Institute as usual. We're set up for the purpose of addressing the issues you guys have been raising. You send us emails, you send us feedbacks, and based on your feedbacks we decided to continue our series and address most of your problems. Now, Go-Gate Engineering Institute, remember, it's an institute that was set up for the purpose of addressing the numerous issues associated with structural engineering. Okay, so when we refer to numerous issues, we refer to design of deep water structures, fluid kinematics, structural retaining structures, structural geotechnics, structural dynamics, first order, second order linear elastic analysis, plastic analysis, and all types of structures. So today we want to look at the design of box culverts. We want to look at the analysis and design of box culverts with Staad. The first thing we need to look at, this is a practical problem, and this is a problem that is always reoccurring in structural engineering. So this is a live project, and this project we are going to use this as an example to explain the process of design of a box culvert. So firstly, let's look at the statement of the problem. What you can see on your screen is a very long span terrain. Now this road extends from chainage 0, so this is where we decided to survey this road, to chainage 2.125, so it's approximately a 2-kilometer road. Now this road, if you look at the contour survey, the road has completely failed as a result of erosion. So the road is facing very severe gully erosion. So if we clearly look at the spot elevation, so this is a contour survey that was done on the entire terrain. If you look at this contour is showing that the spot elevation is 150 meters. This is the reduced level. And then if you look at the contour here, okay, obviously, so the contour has a consistent chainage of 1 meter, so it has a consistent difference of 1 meter. So that's, if you look at this, and that is showing 150, so this automatically is 151. Okay, so this shows the level of undulation on the terrain. So it varies downwards, so you have 151, you have 149, 148, and all of that. So the terrain is very, very steepy. It has consistently failed as a result of gully erosion, so we can observe the effects of the erosion on the road. Okay, so the purpose of this training session now is to explain the structural design of the culvert. A lot of analysis was done, the design of the road was done, the design of slope stabilization structures was also done. If you remain on our page and continue to follow us, we will explain the processes that we follow through in the structural design of the retaining structure. But for now, we want to concern ourselves with the structural design of the culvert. So let's explain the process that we follow through. Firstly, this culvert, the first thing we need to do is to develop your load calculation sheet. Now the culvert is located at chainage 2.1. Now if you look at a transverse cross section of chainage 2.1, okay, so a transverse cross section of chainage 2.1, so this is a transverse survey of the road, right? That's the center of the road, that's to the far right, that's to the far left. So it shows that the road, the terrain varies for about 2 meters. That's 148, and then that's 150, and then that's 152. So roughly about 2.5 meters you have a difference in topography. Now when we visited the site, we saw that the culvert, existing culvert, as a result of the gully erosion, has caused the culvert to fail. Okay, the erosion had caused the culvert to fail, and then we have the obligation to redesign this culvert so that vehicles can take advantage of the road, to move from one location to another. So what are the requirements you would have to follow through in the structural design of the culvert? The very first thing is to carry out a subsurface investigation to obtain the gravimetric properties of the soil and the shear strength properties, in addition to the index characteristics of the soil. Now, we had carried out that survey, we had carried out that subsurface investigation, and we obtained the gravimetric properties of the soil, some of which have been listed here and that you can see on the screen. So we have the bulk unit weight of the soil, we have the specific weight of the soil, we have the specific weight of concrete, that of water. The safe bearing capacity is that. The start chainage of the culvert, so the culvert starts at a certain chainage and then it ends at a certain chainage. So the culvert is at a certain location, so it's at chainage 2.1 kilometers. If we want to make reference to that, we can always see that that's the chainage where the culvert is located. So this is the field culvert that we intend to redesign, right? Is at chainage 2.1 kilometers, that's 2,100 meters. Okay, then we need to determine the soil properties. We have the angle of shear resistance from soil investigation and soil testing, laboratory testing. We obtained the angle of shear resistance from a triaxial compression test. We obtained that to be 6 degrees. The Poisson's ratio was obtained to be 0.472 and all of that. So this is the input information that we gathered from site, from soil testing. Remember, we went to site, we carried out several Atebak limits and index tests on the soil samples that were collected on site. So we have particle site distribution analysis was done, triaxial compression test was done under consolidated drain, consolidated on drain, and unconsolidated on drain, conditioned by, applying a triaxial. Lateral stresses, okay, we applied lateral stresses on the confined soil sample and then failed that by the application of deviator stress to be able to obtain the more circle column failure plane. So based on these information, we then decided to proceed with the structural design of the culverts. Okay, so let's look at the loads that apply in the design of a culvert. The first thing you have is, so you have your trial culvert size. You have your trial culvert size. Typically, before you commence the structural design of the culvert, you need to do an hydraulic sizing of the culvert, using Cheese's equation or Manning's equation to determine if the cross section is suitable, to carry out to transfer the runoff waters. So after carrying out the hydraulic sizing of the culvert, the next thing to do is to perform a structural analysis of the culvert to ensure that the culvert has suitable strength to resist the biaxial stresses occasioned by the imposed loads that the culvert will be carrying. So let's look at the loads that the culvert is going to be carrying. So the first one we have the self-weight of the culvert. Let's look at a typical cross-section of the culvert. Okay, so this is a typical cross-section of the culvert we intend to design. The culvert is designed to be removable. So we have the lead culvert cover. It's designed to be removable, okay, because there will also be certain maintenance that will be done periodically, right? So that's the wall and that's the base. Okay, so the wall is about 225 millimeter thick. The overall depth is 1.35, and then the base is 0.25 meters thick, right? Okay. So the first thing to do is to get the self-weight of the culvert. So that's the specific weight of concrete times its thickness, right? The culvert has a wing wall. Okay, so the weight of the wing wall will also have to be calculated. So this is the wing wall we make reference to. Okay, so it has a wing wall that projects beyond the terminal location of the culvert. So if we look at this drawing, you would see that this is where the culvert terminates, and then we have a wing wall, okay, which is also going to form as a retaining structure because you have soil on both sides, and then the culvert slopes gradually to an existing drain. Okay, so you get the weight of the wing wall the weight of the base, and then the weight of the fill above the culvert. So you're going to have the culvert final elevation is such as that you're going to have some soil fill. So the road level, okay, is 0.5 above the top of the culvert. So the weight of the soil above the culvert is what we estimated to be 9 kilonewton per meter square. This was obtained by multiplying the specific weight of the soil by the thickness of the soil. So these make up the dead weights, okay, that the culvert will be subjected to. The imposed load is calculated as follows. One, you have the vertical intensity of the surcharge. Firstly, we omitted the information that these culverts, the HA and HB loading, these are the vehicular loads that the culvert will be subjected to. HA loading are typically equations used to idealize, normalize vehicular loads in Great Britain. Okay, so these are equations used to idealize normal vehicular loads in Great Britain in compliance with BS 5400, right? So these are HA loading. So HA loading and HB loadings, okay, are calculated as follows. So the vertical intensity of the surcharge, okay, is taken as 10 kilonewton per meter square. This is in compliance with the code requirements. Okay, so the code specifies that the vertical surcharge should be taken as 10 kilonewton per meter square, and then the lateral surcharge is a function of the equation of active earth stress. So this is the vertical intensity of the surcharge. So these are imposed loads that would occur as a result of vehicles passing through or passing over the culverts, right? The vertical intensity of the surcharge for HB loading is taken at 20 kilonewton per meter square. This was referenced from the code accurately. So HB loading for 45 units of HB loads. Note that HB are abnormal vehicular loads that are expected to traverse a roadway. Okay, so abnormal vehicular loads like self-propelled modular transport trucks and heavy-duty vehicles with significant axle loads are what are classified under HB loading. These are massive trailers that carry transformers, they carry equipment, for the purpose of installing at a different location. So these are HB classified loads, right? So the live loading associated with that is taken as 20 kilonewton per meter square as specified by the code. Now the equation of active earth stress is calculated in line with Rankine's earth pressure theory. So Rankine's earth pressure theory is a theory that is used to determine the failure surface of a soil mass, assuming that the interface between the soil and the retaining structure is frictionless. Now the minimum inclination of the failure surface and that derivation would provide a equation of active earth stress expression as shown above. So it's a function of the angle of fill and the angle of shear resistance of the soil. So it's this expression you see where alpha is the angle of inclination of the fill respect to the horizontal. In this case is 0 because we are filling the culvert. Okay, the culvert is going to be filled above. Then the final formation of the road surface assumed to be horizontal. Okay, the wall of the culvert is going to receive lateral earth stresses. Now the equation of active earth stress is calculated as follows. Now once the angle of inclination is 0, this expression automatically becomes 1 minus sine alpha all over 1 plus sine 1 minus sine theta all over 1 plus sine theta. So with that we calculate the lateral surcharge pressure, which is the equation of active earth pressure times the vertical pressure. So this is vertical pressure. We get the corresponding lateral pressure for HA loading and then lateral pressure for HB loading. Okay. Now the active earth stress, okay, associated with the soil. So the soil is going to be cohesionless, so we're going to fill eventually after excavating with cohesionless, which are granular materials. So the active earth stress is equal to the coefficient of active earth stress times the bulk unit weight of the soil, and then times the overall depth. Remember that the height of the culvert is taken as 1.3. 1.3 to the base, right? That's the height of the culvert. The passive earth stress. So once the soil moves into the culvert, the soil mass on the other side of the culvert wall, mobilizes its passive earth stress to counter the effect of the soil movement, right? So the coefficient of passive earth stress is used to calculate the passive earth pressure. Now for HB loading, so this is the loading, the normative philosophy of HA and HB loading. Now in compliance with the code, this is the loading pattern for HB loading, right? So the culvert is going to be on this location. The length of the culvert is about so the length of the culvert occupying the roadway is about 8 meters. So because it is 8 meters, you would have sufficient wheels straddling the entire width of the roadway. Note that this is the width of the HB vehicle, and then so this is the axles, and then these are the wheel loads. Now each wheel is separated by 1 meter, and so you have about 3 meters. So you would have at least 2 HB loads occupying the entire length of the culvert. So this is going to be applied as they are on the culvert. So you're going to see how we're going to do that in a very short while. Now in compliance with section 6.4, the HA wheel loading on the box culvert is taken as 100 kilonewton per wheel. So the code specifies that the application of HA loading is such that you either apply HA loading based on a knife edge load and a uniform distributed load for spans 30 meters and less, or conversely you apply a wheel load that provides a distributed load over an appreciable surface of 1.1 newton per millimeter square. So this wheel load is what we are going to apply on the culvert, and we're going to see how that is going to be applied in Staad. So the next thing is to develop your model in Staad. This is the culvert. What do you do usually when you want to develop your model? You must ensure consistency in your modeling. So this is the culvert. This is the culvert we intend to design. If you look through, you can see that's the wing wall as specified. That's the cover of the culvert. That's the base, and these are the corresponding dimensions. So this is about 250, if we could recall, and the cover is 225. The wall is also 225 millimeter thick, and so the wall and the cover is 225 millimeter thick, while the base is 250 millimeters thick. So you develop your analysis model for the culvert. So the analysis is such that we are carrying out a finite element analysis of the model. You must ensure that your finite meshes based on finite element analysis theory are approximately of equal squares. So they should be, as much as possible, approximately equal squares. So if you look at what we have for the finite elements we have developed, they are approximately equal squares. So the first thing is to develop your analysis model correctly. You inspect your model for accuracy in dimensions. So let's verify that our dimensions are correct. So that's 8 meters, so that's correct. So we provide the member properties. So for the for the wall and for the culvert cover, they are all 2 to 5 millimeter thick, and it's concrete. You provide the isotropic properties of concrete, elastic modulus, Poisson's ratio, and modulus of rigidity accurately. The base of the culvert, the thickness is 250 millimeters, applied correctly. Okay, so the projection, so the wing wall, the perpendicular wing wall, or rather the longitudinal wing wall, is taken as 150 millimeters. The next thing is to provide certain specifications. You could recall that we said that the culvert is designed to be removable. So if it is designed to be removable, you must specify the appropriate releases that will simulate the condition that had predicated the design philosophy. Now, the culvert cover is designed to be removable. Therefore, you must release the joint, the nodes of the slab cover. You must release it for bending about the local principal axis. So the culvert is released for bending about the local principal axis, which in this case is the y direction. Let's look at it carefully. So you can see that's the y direction, that's the x direction. So we release it, okay, for bending about the local y axis, so as to prevent any form of distributed moment transfer from the cover of the culvert to the wall of the culvert. Okay, so that's the releases. You do that correctly. Then we move straight to the loading. Okay, so firstly, the self-weight of the culvert. So by specifying a self-weight parameter, automatically Staad calculates the self-weight of the entire structure. So we selected the wall, and we decided to calculate the self-weight of the cover and the base by ourselves. Remember, we said we calculated this separately before. Dead weight 5.4 for the cover, and for the base is calculated as 6 kilonewton per meter square, right? So that's a 5.4, and the base is 6 kilonewton per meter square. Weight of soil backfill is 9 kilonewton per meter square. We have that applied above the culvert because it's going to be, backfilled after casting and curing. Then we backfill with soil, compact, and then do the road surface. So that's minus 9 kilonewton per meter square. Now, the HA vehicular loads. Let's look at this very carefully. So these are the lateral surcharge. So this is the lateral surcharge loading. Okay, so if you look at this, you see you have lateral surcharge loads on both sides. So this surcharge load is as a result of the vehicular HA loading. Okay, so lateral surcharge load is obtained by multiplying the coefficient of active earth stress by the vertical surcharge. So that provides lateral surcharge as a result of vehicular loads, moving along this side or that side. Next thing you have is the surcharge associated with HB loading. Okay, so when we have HB abnormal vehicular loads, traversing this location, then this is the lateral surcharge that will be applied on the wall of the culvert. Okay, active earth stress. So this is the active earth stress. Okay, so due to the fact that the soil to be filled on the sides of the wall are cohesionless, so the active earth stresses, okay, varies linearly. So you apply the active earth stress on wall 1, and that's the active earth stress on wall 2. Okay, so that's the active earth stress on wall 2, and this is the active earth stress on wall 1. Okay, so similar pressure intensities. Okay, similar pressure intensities. The next thing is the passive earth stress. So where you have active air stress on one side. If vehicles are passing on that side and generating active air stresses on the wall, automatically passive air stresses are mobilized on this side of the wall. So you need to calculate the passive air stresses on both sides. So if you mirror the scenario, if you have vehicles coming here, you will have passive air stresses on that side of the wall. So you have, this is the passive air stress on that side. Okay, next thing we have is the HA loading. Let's look at carefully what we did for the HA loading. How did we apply the HA loading? Let's look at that carefully. Okay, okay, so the HA loadings are applied based on the fact that we have assumed that we would have two vehicles. Now this is one vehicle, that's another vehicle, that's another vehicle. So three vehicles can occupy the entire culvert length at once. Okay, so we have an offset of about 1 meter, right? And then this is the width of the vehicle. So this is one vehicle, that's another vehicle, that's another vehicle. So three vehicles can conveniently occupy this culvert. So this is a very critical scenario that you have to simulate in your analysis, right? So the vehicle must be, the wheel load from the vehicle has to be applied on the centroid of the culvert cover, okay, which is a very critical influence line for the failure stresses on the culvert. Okay, so that's what has been done for the HA loading. Right, for HB loading, so recall that the code specifies that for HA loading you must apply a load intensity over an appreciable area that provides a pressure load from the wheel of about 1.1 Newton per millimeter square. So this is what has been done. Note very carefully that this design is done in compliance with BD 3701 and then BS 5400. Okay, so these are the requirements. Now this is HB loading. Look at one typical unit of HB loading. You know, if you look at one typical unit of HB loading, you have the spacing of the axles as 1.8, and then correspondingly the next set of axles can either be spaced at 6, 11, 16 and so on. Right, so each wheel provides a concentrated force of 2.5 kilonewtons. Now this has been calculated and applied correctly in Staad. Look very carefully. So what we have here is that, so what can straddle this entire culvert, okay, conveniently is two sets of HB loading. So that is one HB loading, that's another HB loading. Let's look at this and understand how this was applied. Okay, so if you look at this, the width of one HB loading, you have about 1, 2, 3, 4. You have two axes on that side, and then you have 4 wheels. So those are the 4 wheels. Okay, each wheel is spaced at 1 meter correctly, as the code specifies. Now the code states that you must apply this wheel load over an appreciable area that will provide a load intensity of 1100 kilonewton per meter square. This is specified in the code, and that has been calculated and applied accurately on the culvert. Okay, so in the design of a culvert, whatever span your culvert is, you must always ensure that the most onerous representation of the loadings that the culvert would carry must be catered for. So we could have one HB and one HA passing here. You could have 2 HBs passing here. So this has been catered for. Okay, this catered for 2 HBs. Right, so you have one HB loading and you have another HB loading. So 2 HB loadings, you know, has been catered for in this design. Then you proceed with your load combination. So we have so the load combinations provided for in this design is also captured clearly in the code. 5400 makes requirement for load combination. Okay, so it tells you table 1 gives explicitly the partial factors of safety to be catered for when applying load combination. So we have dead and life, and 1, 2, 3, 5, and 9. So we have the self weight of the culvert, you have that of the backfill, you have that of the surcharge. So if you look at the way this combination was done, you have the dead load and the backfill as one. So 3 and 5, you have surcharge load, active earth surcharge, and then you have to look at 3 and 5. So you have lateral surcharge and active earth stress together, and then you have 9 and 8, you have HA and passive earth stress. So this load combination catered for the fact that you have just one HA vehicle passing over the culvert, and then it generates an active earth stress on one side and generates a passive earth stress, a corresponding passive earth stress on the other side. So if you look at that load combination, so it represents the effects of one HA vehicle passing and the corresponding force interaction that the culvert will be subjected to. For load case 200.67, so it looks at the same scenario. So load case 100 caters for that scenario on one side of the culvert. Okay, so active earth stress here, passive on the other side. 200 is a mirror representation of that. So you see, so 1, 2, 4, 6, 7. So 6 is active earth stress, okay, on wall 2, right? And then 7 is passive earth stress on wall 1. So you have active earth stress there, and then passive. You must alter your load distribution, must represent the nature of forces that the structure will be subjected to. So when you have active earth stress there, you have passive earth stress on the other side. Okay, so that load combination caters for that, together with the HB loading. So these are the stresses associated with these are the forces associated with the HB loading. Okay, these combinations are clearly defined in the code. The code specifies how these combinations should be applied. Okay, so this is the code that we are making reference to. Okay, so it's listed here carefully: the dead load, the superimposed dead loads, temperature loads, and all of that. Then so these are serviceability limit state loads 1 and 2. 100 and 200 and 300 and 400 are ultimate limit state loads, which are used to check the strength of the culvert. Okay, suitability of the culvert to biaxial flexural stresses, shear stresses, and the like. So as soon as you're through with this, you perform an analysis, and you run the analysis. At the completion of run, you go to your post processor, you look at the load combinations. So 1 and 200 are serviceability limit state load combination. One of the things you need to look at is to ensure that the maximum earth stresses is not more than the alignment capacity of the soil. For this design, the alignment capacity of the soil was calculated as, so the safe bearing capacity of the soil. So safe bearing capacity of the soil is the foundation pressure that will prevent the underlying soil to fail in shear, but settlement would not be satisfactory. So you may need to calculate and calculate the effect of settlement as a result of the most onerous load combination. So the safe bearing capacity of the soil is taken as 120 km square from the geotechnical investigation report. When we look at the analysis outcome, let's go to the for the two service load combination rather, you go to base pressure. You can see that the maximum earth pressure we can see is about 53.8 km square. If you look at that again for load case 200, we can see that the maximum earth pressure is 35. So what is controlling is load case 100, which is the most critical for the service limit state. So the maximum earth pressure is 53.8, and that's less than alignment capacity of the soil. So the culvert is satisfactory. Okay. We will proceed with the design of the culvert in our subsequent section. Thank you. And always, follow us on this page, on this link on Go-Gate Engineering Institute. We would always address your concerns all the time. Thank you very much.